Good morning, everybody. I hope that Gael woke you up. I think so. Enough provocative to wake everybody up. So my name is Alex Granford. So I'm coming from very, very far, almost San Francisco, but pretty much the second building from Telecom Paris, which is where you are right now. So I'm actually assistant professor here, teaching machine learning among other stuff. And I've been a core developer of scikit-learn since the beginning, since 2010. And I'm also one of the few people who are trying to build this Paris-Saclay Center for Data Science that tries to bring machine learning to applications in science and industrial problems. Better? Okay. So if you want to find me online, that's pretty easy, actually. So the goal of this gentle intro talk is to familiarize you with linear models in scikit-learn. So basically, see with simple toy examples to almost real applications how scikit-learn can be used with linear models and when to use it. All right, so where do we stand right now? So I'm going to start with this simple ML taxonomy. So Gael actually already introduced you this concept of unsupervised and supervised learning. What I'm going to talk to you about this morning is supervised learning. So when I say I want to predict something, that's where prediction and supervised learning comes in. And there are different supervised learning problems. The two very classical ones are regressions and classifications problems. But there are some others like ranking, for example. And there's plenty of examples in the real world. So we are at PyData. There's a lot of industrial problems that may be of interest to you. That could be prediction consumer churn. So if your client is likely to leave the service that you're trying to build or building, you want to predict traffic, the failure of an equipment, some price of online things. You want to predict the bid for an online ad. And you want to predict, for example, spam or ham, which is a very simple real-life example. So at the end of the day, all these problems end up being a problem of the form, give me X, and I will predict Y. So give me data, X will be what we call the data, and Y will be what we call the target. Okay. I think at the end of the day, like 4 people who have to tell you the same thing, it's going to be super clear that you go from X to Y. And this can be done either with a linear method or a nonlinear method. I'm going to focus now on linear methods and show you examples where it actually can be used. And I guess Gilles afterwards will talk to you about the decision forests, and which are typically nonlinear things. Well, you might wonder, can I solve any real problem with a linear model? And so can the world be considered a linear in some context? I'm going to try to convince you that it's there are reasons why you probably okay. So there are actually applications where linear models will be the winning solutions. So let's start with a very simple toy data, which is one of the data sets that we ship for with scikit-learn for examples and demonstrations, which is the Boston dataset. So it's a very old machine learning dataset that consists in predicting the price of houses in Boston. So if you import, if you load the load Boston function from the datasets module in scikit-learn, you have this function that you can call that will give you as output the Boston dataset, which contains a different number of attributes. The first one would be desc, which stands of course for descriptions, which tell you what this dataset is. And here it's in Boston house prices. You have 506 instances. So this is the samples that Gael mentioned. And we have 13 numeric and categorical predictive features. So we have 13 variables that are going to be used for prediction. Okay. And among these variables, you have this CRIM, ZN, which is per capita crime rate per town, and a bunch of other variables, which are going to be used for prediction. Okay? So if I now go a bit further with my Boston object here, it has two attributes, which is data and target. So my data, again, is going to be X, and my target is going to be Y. The game is, give me data, I will predict the target. If you'll give me X, I will predict Y. So X is a NumPy array. Okay, so NumPy arrays have a shape attribute, which tells you the number of rows and columns. The rows will always be the samples, and the columns will be the features. So if I do x.shape equal n samples and features, I recover my 506 number of samples and my 13 features. Okay, and I can also look at the feature names attributes from the Boston object, and it will tell you crim, zn, indus, blah, blah, blah. Okay, and I've got 13 of these things, and this is actually a pure Python list. Okay. And so let's first, so when you have a data set and a real machine learning problem, the first thing you need to do is look at your data. So let's start by this, and let's look at what we're trying to predict, so the target. So if I just look at the histogram of Y using matplotlib, I've got this histogram that tells me what's the price of the houses in thousands of dollars. It's actually a pretty old data set. The prices are much more expensive these days. And this is the label here, the price. All right? So now we know what we were trying to predict. Let's try to figure out what we're going to use to do this. So we can look at the targets. There's a pretty easy way to do this using pandas. You'll have a nice intro to pandas afterwards. But I just use pandas here to produce this fancy table that shows me very quickly what's the content of my table. So the crim, what's the values, Zn, indus, etc. Okay, so this is my data, and I can further use pandas to explore it, and I think Joris will give you a start on this. All right, so now I'm jumping to this notion of linear models. So what does it mean to have a linear model? It really means that what you're trying to predict, which is the variable y, can be expressed as a linear function from the data. So here we have 13 values per sample, which are these 13 variables. So if I use a linear model, what I'm going to say is that the output y can be expressed as a linear combination of θ0, which we'll call an intercept, θ1, which is the coefficient for the first feature, and θp will be the coefficient for the last feature. And the price here in this particular case can be said to be equal to θ0, θ1 times the crime value, θ2 times Zn value, θ13 times LC value. Okay? So how do I instantiate this with scikit-learn? So the linear models are almost exclusively in the linear model module. So if I do from sklearn linear model import the first vanilla linear model that you might think of, which is linear regression, I can do this from sklearn linear model import linear regression, and then I have my model that I instantiates with the default parameters. Okay, so every estimator in scikit-learn has defaults. Okay, doesn't mean that they're always the best, but it means that it should always work out of the box. And how do I fit my linear model? Simply by calling the fit method with x and y. Now in scikit-learn, everything that is learned from the data ends up being stored in attributes of the instances with this convention of the trailing underscore. So the coefficient will be in the coef underscore attribute, with shape is 13, and the intercept, so the θ0, will be stored in the intercept attribute with the trailing underscore. It also means that if you have an instance of a scikit-learn estimator, you look at the attributes. If it ends with the trailing underscore, this is data-driven. This is obtained from the data. This is estimated. Okay? And I can fit my model now on every even sample and predict on every odd number, every odd sample, so making sure that I don't predict on the training on the training set to avoid overfitting. And just calling the score method, I end up with an R2 score of 75%. Okay. Doesn't mean that's the best thing you can do. It's just a very simple example to familiarize you with the API. All right. So if you're curious about what's in the linear module, you can just use dir or tab completion in IPython. And here I just do dir linear model, and it lists a bunch of classes or estimators that are available in the linear model module. ARD regression, ElasticNet, lasso for sparse regression, linear regression we've just used. We'll see it right afterwards, logistic regression, but you have a bunch of others. they all respect this fit predict score API. All right, so if you want to try another model, if you basically followed up to now, you just need to change one thing, which is how do you call a classifier? Here, if I call it ridge, that instantiate my ridge model, and I just change this line, and that's it. Okay, so if you want to explore experiments with different estimators, you just have these two lines to change. Okay. So, how do I go from linear models to a classification problem? Well, if you just have a binary problem, it's super simple. You just use the sign of this linear combination of the features, and if the sign is 1, meaning if your linear combination ends up with a positive number, you predict 1. If it's a negative number, you predict -1. So imagine that 1 is the spam class, and -1 is the ham class. Okay, so give me all my features, use a linear model. If my value output is positive, I will predict it's a spam. If it's negative, I will predict it's a ham. Okay? So, in 2D, what does it tell you? So if I've got two features, two explaining variables, x1 and x2, it basically says that if I'm on this side of the hyperplane, because this defines a hyperplane, so a linear separating object, if I'm on this side, I'm going to be of class 1. If I'm the other side, I'm going to be of class -1. Okay? So now let's play with this on a classification problem. The other data set that we have in scikit-learn for examples for classification is IRIS. Again, a very classical machine learning data set. Here I'm just going to use the first two features in order to visualize it. I'm going to use only the first two classes because you have 3 classes in this data set, and I'm going to assign the value -1 to the class 0. Okay, so this is plain NumPy code. There's not really any scikit-learn specific things. It's just applying vectorized NumPy operations. And at the end of these 4 lines, what do I have? I've got x, which is 100 observations, 100 samples, and I've got 2 features. And if I look at the number, what are the unique values in y? I've got 2 values, -1 and y. Okay, so 2 features, 100 samples, output 1 and -1. I want to learn how to predict in this setup. So this, if you do a plot, this is actually the IRIS data set on these 2 features. And what you hope to obtain by using scikit-learn is a linear separating function that goes along these 2 sets of points. Okay? So let's see if we can make this work. We're going to use the logistic regression object, which is a classifier, a linear classifier, and instantiate the model, setting the regularization parameters, and then we fit, and we again get an intercept attribute and a coef attribute. Here you might wonder why I had to do this square bracket 0, because if you have a multi-class problem, you might have multiple hyperplanes. But that's beyond the scope of this story. And here I've got my θ0 and my θ, okay? And if I actually plot what these values tell me about the data, that gives me exactly this hyperplane that you see here. And you might wonder, why is this green dot not on the right side of the hyperplane? It's basically because I regularized my problem, and my logistic regression problem, my logistic regression algorithm basically did not overfit completely the training data. So this point is actually mislabeled on the train. So I don't have 100% accuracy on my training data. Okay. And if I want to do a support vector machine, okay, using a linear model, so I told you not every linear model is in the linear model module, because typically SVM can be also nonlinear. So to avoid splitting the code everywhere, you still find some linear SVM in the SVM module, but it still respects the same API. Okay. So here in 4 lines of code, you've trained your first support vector machine. Now let's jump into a more real-world problem. So I took this data set from a fairly old now Kaggle competition from 2012, where the goal is to predict from comments on a social website. It's like social commentary on the social website, if the comment was actually an insult or just a friendly comment. Okay, so this is plain text, and we're going to use a linear model to predict if it's a nice comment or not so nice comment. So if you look at the train CSV file that is provided by the website, you have the first entry, which is the class. So here 0 means it's a friendly comment, or actually not an insult. And then the raw text. Okay, so the game is going to be say that this is my data. So my X will be the form of a plain text, a set of characters, a string, a Python strings actually, and with the attached label. Okay. So I'm going to write 4 lines of Python to actually parse this text file this way. So for every line in my file, I will take the first value that will give you my class, and then removing the first 3 quotes and the last 3 quotes, I'm going to be able to get the plain text. And at the end of the day, what I have is a Python list. So X is actually a list with more than 4,000 entries, which is the 4,000 comments that are used for training. Okay. And here my Y is going to be a set of 0 and 1 if I'm more an insult or not. And here, if I just look at the first value of my list, so slicing my list, just taking the first entry, I get this list with a Python string. Now I'm going to use 11 lines of scikit-learn code to go from the text to a model that actually can learn from it. So I'm going to use a linear model, my logistic regression, and I'm going to use a vectorizer that is adapted to text that I have here. And I'm going to use a feature selection, which is actually a transformer using a chi-square function. And I'm going to use a pipeline to assemble all this, and then at the end of the day, create my classifier that I'm going to use for classification. So the way it works, I've got my transformer here, which selects 16% of the best features using a chi-square discriminative scoring function. I've got my logistic regression, and I've got 2 vectorizers that are based either on plain characters or just words. Okay. Then I'm going to do a feature union, a union of the character vectorized or the word vectorized. And then I'm going to make a pipeline that will do feature transform, selection, logistic regression. And at the end of the day, what this make pipeline gives me is an object that will respect the scikit-learn API, which is fit, predict, transform, score. Okay. So I can use cross-val score to evaluate the performance of my model. So cross-val score with CLF, X, Y, and CV equal 2 to do a 2-fold cross-validation. And if I just do the mean score of these 2 folds, I get 81% accuracy. So you might wonder is, where would I have been on the Kaggle leaderboard with 11 lines of code? Well, you wouldn't have won, but you would have been just after Andy, who's here. So Andy is has been the release manager of scikit-learn for the last 2 years now, and actually a very active contributor to the project. So this is an occasion to do a demo of scikit-learn and also give credit to Andy, who is doing an amazing job on scikit-learn. Okay, so you're not winning, but you're really close, and what you basically wrote is 11 lines of code, so you can actually quickly evaluate the value of your data. And you might wonder, did it take me time? I mean, are we efficient with these linear models? Well, if I just do a transform of X, here getting the number of samples of features after transforming, you see that the transform that goes from text to my numeric data, numeric array. So X is actually here, not a NumPy array, but a SciPy sparse matrix, but that's beyond the scope. But actually has a lot of columns, so 226,000 features. So this is the number of columns, and here the number of rows of your objects will always be your number of samples. And if you use logistic regression like we've done, and we apply it to this XX, how much time does it take on actually the laptop, like you would have exactly here? It takes 2 seconds of computation. Okay. And you can actually do better if you reduce the tolerance or if you change slightly the algorithm. But again, I don't have much time to do this, but it's actually pretty quick to train. Okay. So now, what if your data don't fit in memory and you want to go out of core? So Gal actually told you a bit about this just before. But the idea is to give the data chunk by chunk to your estimator using this partial fit method. So rather than calling fit up to now, I'm going to call partial fit on subsets of my data that are small enough to fit in the RAM of my laptop or my desktop computer. And here I'm going to use a very cool feature from Pandas, which allows you to read from a CSV file by chunks. Okay. So here I've got my data. Imagine your data is in data.csv. If I just do iterate on the output of this read CSV from Pandas, I will get 20 rows by 20 rows. And I'm going to get the target from my data using the values, and I will get the values from my Pandas data frame after dropping the target to avoid using the target for prediction, which would be actually a bit cheating, and using partial fit. So two things to take a look: a chunk of the data and partial fit. And if you do this way, it basically means that you're not limited anymore by the amount of memory that you have on your machine. All right. So there's a lot of estimators that support this partial fit. So if you take the scikit-learn code, you just do git grep partial fit. You will find all the partial fit occurrence in the code base. Or if you look on the website searching, you will find all the estimators that support this out-of-core online API. And there's also a very nice example on a big-ish text dataset from the Reuters dataset that you can find on this address. At this address. Okay, so now you might wonder, what if my linear model is not enough for my data? There's something which probably not the optimal thing you want to do, but that works quite well on some applications, which is just to add some nonlinear features to your data. And just imagine your data looks like this. This is a typical 2 moons data set that we have in machine learning, where you have a class 1 that looks like this red moon, and the class -1, which is the moon on the other side. So there's no way you can classify these 2 moons with a linear function. So this would be what the linear function would tell you. So if I use my logistic regression on this data set, I get this 80% accuracy on the train, and it's very likely to be the same performance on the test. So not optimal, and you clearly see that you can do better. Well, there's a very cheap thing that you can do, an easy thing, which is to add polynomial features. So if I just do a pipeline and I add polynomial features, so basically I take all my features, I square them, and I also add the interaction terms, again fitting my logistic regression, I will have this quadratic separating function. And if I just go one step beyond using polynomial features of order 3, you see your boundary function that looks like this, and you've increased your accuracy on the train. So remember that if you do this on real data, what you're interested in is the performance on left out data. So the more you add nonlinearities to your model, training model, the more likely you overfit. So you should basically calibrate this on your particular data set, but you can go from these nonlinear models to linear models to nonlinear using this. And imagine that you take your data now by chunks. You take the data by chunks, you create the nonlinear polynomial features on a subset of the data, you feed it to the online estimators. You can really scale with a nonlinear classifier this way. Okay, so let me wrap up. So when do you want to use a linear? So the first answer is, of course, if your data is generated by a linear model, which, to be honest, is rarely the case. But you never know. Or when your data is actually, in the case of classification, when your data is really linearly separable. And also when you test with nonlinear models with cross-validation, and you realize that you massively overfit when you use a nonlinear model. And this is typically happens, these scenarios happen when your number of observations, your number of samples is smaller or much smaller than the number of features. So this happens in a few applications. And this is precisely when the linear models will perform well. When we played with the text data, this was typically the case. We had 4,000 samples. We were projecting the data to a huge dimensional space by using these word countings or character countings, and the linear models were pretty efficient. And of course, because they are simple and efficient. So if you want to know more about the linear models, you can go to this documentation, which is specific to the linear model module. And let me just conclude by saying, like Gail said, that I'm looking for people with passion for open source and machine learning and the simplicity and the beauty of Python. So if you're interested in working on these things here in this institute, please send me a tweet or an email. And thank you for your attention.